There we go. All right, good morning, everyone. Um, the plan for today is I want to do one problem related to lines, just as a bit of a, I don't want to say refresher, but maybe a bit of a review, because I did put the lines video together for you to watch so that you can get started on the homework assignment. But I'm happy to go over a particular question on lines, and then we'll get into planes. And the idea with planes is these are objects in 3 dimensions. How can we represent them? How can we talk about them? And for example, how do we know that an equation of the form x equals z is a plane? We'll start to see that in this section, we can determine that that is a plane in a much easier way than we could have determined it was a plane from a prior section. So we're going to get into the heart of the matter of what are planes and how to describe them. So let's start with a warm-up problem. So what I'm going to do is I'm just going to post in the chat a link, and feel free to go ahead and click that link. It'll open in your browser window to a page called Mathematize. And once you open that link, it'll probably say no exercises are active. Please wait for your instructor. So I have a bit of a warm-up exercise here that's a poll question. Completely anonymous. As you see, you didn't log in or anything, so it's just anonymous, but just for fun to get warmed up. There's a hand raise. Yep, go ahead.
Yeah. Did we skip the past 2 pages?
Those were delegated to a video. So I did a video lecture on the first 2 sections of lines on the Friday and posted it so that you could get started with lines for the homework assignment. So if you haven't watched the video yet, that's available in the lecture notes section. So go ahead. You don't need to watch that now before the planes. In some sense, the lines and planes are sort of disjoint kind of objects. At one point today, we may actually borrow on that, but we'll also talk about it. I'll talk about it very briefly in this warm-up exercise. So you can get a quick review of it. If you didn't watch the video yet, you'll get the gist of it from this warm-up exercise. All right, so here's the warm-up exercise. It should be displaying on your screen. I will drag mine over so that you can see what it would say. So determine a vector equation for the line that contains these 2 points. So we got 2 points in 3-dimensional space. Find the vector equation for the line that contains them. And you're also given a bit of a hint here as to what the vector equation looks like. It's r of t is equal to some vector plus a multiple of another vector. So t times another vector, where t is a parameter that's allowed to change to trace out the whole line. I'll give you just a second to think about how you would fill in those blanks, and then I will open up the problem so that you can do a multiple choice selection for each of those blanks. So take a moment to think about how you would do this. All right, I'm going to open it up so that now it's accepting a response. So you can click on either of the blanks and you'll get 3 choices to fill in that blank. And the choices differ based on the blank you click on. So you click on the first blank, make a selection for what you think the vector is, should fill that first blank, and so on for the second blank. What's the vector that should fill in that second blank? If you make a mistake, if you click something and you're like, no, I didn't want to click that, and you rethink them and you thought about it and you thought you make a different choice, easy enough, just refresh the page and it'll reload that question and you're all reset and free to go again. give it about another 30 seconds or so to fire in a response. All right, looks like responses are slowing down. All right, 5, 4, 3, 2, 1. I'm going to stop the poll. And I will show responses. Okay, so you can see your graded response there. What I'm going to do is, so I didn't fully select mine, so I'll just back it up a second. So I didn't fully select all the answers for mine. So you'll see a green box around the response that's correct. You'll see a red box around one that was incorrect. And if you see here, view classroom results, you can go ahead and click that if you wanted, and you can see how everyone in the class did. So it looks like 90% of the class or the respondents got the first part right, and about 83 got the second part right. So let's go ahead and see how we can do this. I'll do it at the bottom of the page. So our question is, we've got our point P, which is not -2, I was about to write -2, it's 2, -3, 5. We got our point Q, which is 0, 1, 1. And so these are 2 points in space. We're trying to find the equation of the line that passes through these 2 points. So if this is, maybe I'll say that's P and that's Q. We need to find a vector that points in the direction of the line. So we could do one of 2 things. I could do P minus Q or Q minus P. So in other words, I could take the vector that starts at P and goes to Q, or starts at Q and goes to P. In the responses, the options I gave you, I forced you to make one of the choices over the other. And that's just because it's a multiple choice system. So it wasn't allowing me to have multiple correct answers. So I had to go with one option, and I went with this one so that we could find the vector tip minus tail. So P minus Q gives us the vector. So that would be 2 minus 0, -3 minus 1 is a -4, and 5 minus 1 is 4. So that's a vector that points in the direction of the line. And now to get to any other point on the line, what we would do is we would start at one point on the line, let's say Q in this case, and then just add to that some multiple of, if I call this vector V, we would add to that some multiple of V to get out to that point. So I'd have to start at Q and go out to V. So if there's an origin somewhere, then the way I would get to it is I'd use the position vector. I'll put Q with a vector symbol on top. I'd go, in order to get to that orange point way out at the end, I would start with the position vector of one point on the curve. Let's call that point Q, and add to that a multiple of a vector that points in the direction of the line, 2, -4, 4. And changing this value of the parameter will get me to different points along the line. And so that is our equation of our line. And as you can see, there's many possibilities I could change. I took this to be Q, the vector, the position vector, but I could have chosen it to be P, or I could have chosen it to be really any other point. It just so happens those are the only 2 points at this time that I knew on there, but I could take that to be Q, or I could take it to PP. So either answer would have been correct. I just didn't give you an option to construct it with the P. Similarly for the vector, this vector could be the vector QP, or we could have chosen the vector from P to Q, just the opposite, so the negation of it. Or I could have taken it to be, or we could have done R of T. So these are all correct answers. They were just not options available in the multiple choice. All I want to know is I've got a point on the curve or on the line, and I want to find a vector that points in its direction. I found the vector 2, -4, 4, but I could have also scaled that and just taken 1, -2, 2. That would have also been a correct answer, because that vector is just some scaled down version of a vector that's parallel to the line. So it itself is parallel to the line. And I can just show you here that what we can do in math3d.org is we can drop the 2 points down. And now that we know how to construct parametric equations or parametric curves or vector equations of the line, we can go ahead and construct that and see that it does indeed pass through the 2 points. If I wanted to test some other ones, I could say plot another parameterized curve. And I'm going to just wipe this out and start fresh. So we can start at that same point, 0, 1, 1. Add to that a multiple of a vector that's parallel to the line. I'll take the 1, -2, 2 vector, because that's just a scaled down version of the 1 vector that I already found in the direction of the line. I'm going to change this to purple, or maybe I'll change it to an orange, just so we can see that it is the same line. You can see them both there now. They live one on top of another. So this is the same line as this one, just a different parameterization or vector equation for it. Are there any further questions with lines? Feel free to shout them out if you have any further questions. So that was, if you didn't watch the video lecture, that was basically the idea of the video lecture, was going through this construction of lines and then doing some further examples. So if you do have any more questions and you haven't watched the video yet, go ahead and do so. And if you do have questions, you can always fire them off to me or post them in the discussion board forum, or send me a direct message. I'm more than happy to chat with you about it. All right, we are done with that instant polling. So I'm going to stop presenting and I will kill that poll, and we will go back to the next part. So the next part of this section is on planes. So what is a plane determined by? So a plane in 3-dimensional space is just determined by 3 points that lie on the plane. So if I have 3 points in space, they're going to define a plane. You can think of this by analogy as if you've got a flat piece of wood, like a piece of plywood or a tabletop, and you want to know how many legs it will take to support it and keep it level so it's stable, you need at least 3 legs. If you had only 2 legs, they wouldn't support the table, because the table would rock or pivot about the line that passes through those two legs where they meet the table. So they would roll along that line. So you need 3 tables to, sorry, 3 tables. You need 3 legs to support a table. And that's just the idea here, that we need 3 points to determine a plane. How else could we determine a plane? So that's just in terms of points. So a plane, so equivalently, how else could we determine a plane? A plane can be determined. Here's where we want to bring vectors into the picture. So we'll think that as a starting point, we've got these 3 points that can determine a plane. In connection with a line, we had 2 points that determined a line. But once we had those 2 points, we could start doing things like construct vectors that are parallel to the line, etc. We can do the same thing here. If I have 3 points on a plane, then I can construct vectors that are parallel to that plane. So there's an example of 2 vectors that are parallel to the plane. And those would be enough to determine the plane along with a point. So a plane is determined by a point and two vectors parallel to the plane. So that's another way we could describe a plane. We could describe it by using a point and two vectors that are parallel to it. Lastly, if we have two vectors that are parallel to the plane, yep, exactly. Similar, so as stated in the chat, it is really thinking about a point and two lines, two non-parallel lines. So there we go, I've sketched those lines in. So yeah, drawing from our discussion on lines, this is really saying that it's determined by a point and two vectors parallel to the plane, or I'll put in parentheses, or two non-parallel lines in the plane. I should really say a point and two non-parallel vectors as well. I mean, to be precise, non-parallel vectors. Because if I said, I consider the plane which passes through the origin and has vector 1, 1, 1 parallel to it and vector 2, 2, 2 parallel to it. Well, I haven't really given any new information with that second vector. And I still haven't defined a plane because I've only given you essentially one direction that has to be parallel to the plane. There needs to be a second non-parallel to completely capture it. So a point and two, to be specific, non-parallel vectors. So that's the two, similarly, the two lines there that lie in the plane. And the third way we can do it is we can think in terms of vectors. If I have two vectors that live in us, sometimes I say live in the plane, I just mean that they're parallel to the plane. So if I have two vectors that live in the plane, then when I take their cross product, that's going to give me a vector that's perpendicular to both of the two vectors that live in the plane. And that vector is going to be a perpendicular vector to the plane itself. It's going to be what we call a normal vector to the plane. And that's enough to determine the plane. So a plane can be determined by a point and a vector normal or orthogonal or perpendicular. These are all synonyms. Perpendicular to the plane. Ran out of room to write the word plane there, to the plane. Again, it's just a little short, to the plane. There we go. All right, so it can be determined by a point and a vector perpendicular or normal to the plane. So that was our orange vector in the picture. So these are all three ways we can describe a plane. We could use 3 points. We could use a point and two vectors parallel to the plane, or a point and a single vector that's perpendicular to the plane. So let's pretend for the moment that we're given 3 points. So here's our 3 points, P1, P2, P3. And we'd like to find an equation of the plane that contains three points. So we'd like to find an equation. So what an equation is, it's going to be an expression which gives us conditions on points to lie on this plane, or conditions on the position vector of a point to lie on this plane. So we want to come up with some condition that captures completely the set of all points that live on this plane. So how are we going to do that? Well, let's just get a feel for the situation by plotting our points. So we got P1, say P2, P3. They're going to define some planes. So we'll sketch a plane in the background that they live on. Maybe something like this. And now I'd like to try to capture For example, suppose I had a point Q that lived on that plane. I'd like to come up with an expression that Q has to satisfy. So what does Q have to satisfy? What do the coordinates of Q have to satisfy in order to be on this plane? So one way we could capture this information, and I want this to relate back to P1, P2, P3. So I want there to be condition on Q, how it's related back to P1, P2, P3 that gives us a complete characterization of when it's sitting in the plane defined by those three points. So what we'll do is we'll start with these two vectors. Doesn't matter which two we take. I'm taking P1 as my common tail for the two vectors, but I could really do that for any of these points. There's nothing special about taking P1 as the common tail. So I'm taking these two vectors, P1 to P2, and the other vector P1 to P3. Once I have those two vectors, I can compute their cross product. And what I'll get is a normal vector to the plane. So that's going to be P1, just to be consistent with the picture here and the right-hand rule. It looks like I'm taking P1, P3, cross with P1, P2. That gives us a vector that's perpendicular to those two vectors. And then lastly, if I draw the vector from that P1 all the way out to Q, so that's our P1 Q vector, then what can we say about the vector N and P1 Q? How are they related to each other? So how are P1 Q, how is the blue vector and the orange vector related? Any ideas? Yeah, the dot product is 0. Exactly. They're perpendicular to each other. So their dot product is 0. So the thing to note is P1Q is perpendicular. So that's our symbol for perpendicular. Perpendicular to N. And then that means therefore, or it's equivalent to, that their dot product is 0. And so we get an expression like this. And this is our equation of the plane. So this is an equation that points Q in the plane must satisfy. So that's our equation of the plane. It's the set of all points Q such that the normal vector to the plane dotted with the position, the vector from this arbitrary point I selected on the plane, P1 to Q, such that the normal vector is perpendicular to the vector from P1 to Q for any point on it. We will unpack this equation in the very next line and make it a little bit more functional for us to use. So that's our sort of abstraction of the equation of a plane. Now let's get down to specifics. So how can we write these equations of the plane? Well, the vector equation of the plane passing through the point given by its position vector r0 and a normal to the given vector n is given by this expression here. It's pretty much the exact same picture we had above. So let's just sketch those details in. We've got this plane. Let's think about what information we have. So we want to find the vector equation of the plane passing through the point given by its position vector r0. So that's a bit of a mouthful, but all that says is we've got a point on the plane. But because we want to work with vectors and not points themselves, the way I work with a point is by its position vector. So I imagine there's a origin somewhere. And so I use the position vector of that point on the plane. So that's our r0 vector. Maybe this is point P, but I'll work with it through its position vector, which is just basically taking the round brackets around the point and replacing them with the angle brackets. around the 3 tuple, and that converts it to its position vector. So we've got our position vector of a point. We also have a normal vector to the plane. And the question is, we want to come up with a equation for various other points on the plane. So if I took another point Q, much like we did above, I want to come up with an expression for what Q has to satisfy, an equation that Q has to satisfy in order to be guaranteed to be on the plane. So what I'll do is I'll draw its position vector. That's our arbitrary point Q. So I'll let its position vector to be R. And now I get the vector that goes from P to Q. That's this vector here. And that vector there is tip minus tail. So this vector is R minus R naught. So again, the idea was to introduce vectors so that we could do operations on them, like addition, subtraction, and that, because we can't do those on points. So we talk about points by their position vectors. And now we've got all the information we need in this diagram, because that point Q lives on the plane precisely when R minus R naught, that vector from P to Q, is perpendicular to N. And that's this expression here. N dot R minus R naught has to be 0 for Q to be on the plane. So this is called the vector equation for the plane. It was basically that equation we had up above, but I use now position vectors for P1 and Q, and therefore could make sense of that expression, the vector from P1 to Q. Now we could go even a step further and make it even more functional for us to use. And the way we're going to make it one step further is I'm going to start to add coordinates in here. So I'll talk about Q as being X, Y, Z. And I'll talk about the point P. The point P could be given by X naught, Y naught, Z naught. So that's our point P. In which case then our vector R minus R naught would be X minus X naught. So tip minus tail, Y minus Y naught, Z minus Z naught. And so that's what this would be. That would be that vector there. Maybe I should draw the arrow so that it kind of points to the whole thing instead. So that's what would go in that slot R minus R naught. It would be the vector given by X minus X naught, Y minus Y naught, Z minus Z naught. And if N, now I'm reading the bottom part of the page, if N is given by components A, B, and C, then that dot product, so then N dot R minus R naught equals 0, it unpacks to A, B, C dot X minus X naught, Y minus Y naught, and Z minus Z naught equal to 0. And if we do the dot product, then that becomes that equation. A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught equals 0. And this is a linear equation. Linear equation in 3 variables, X, Y, and Z. And that's our, as we've discovered through this process, that's the equation of a plane. So a plane in 3 dimensions is like the analog of a line in 2 dimensions. It's given, it's the object that's given by a linear equation. So this linear equation is what we call the scalar equation of the plane. This is probably how most of the equations are going to be given to us for planes. We will be describing them through these linear equations most of the time. What we can do is we can then do the multiplication. So A can multiply through the X minus X naught, B can multiply through Y minus Y naught, and so on. The X, Y, Z is the variable. That's this arbitrary point on the plane we're trying to capture. X naught, Y naught, Z naught are constants. That's the point we know on the plane. So if I can move all the constants to the right-hand side, then I get an equation like the one written here, where the D is just the AX naught, BY naught, CZ naught moved to the other side. There was a mistake in the notes. I think it might be in yours. There was a minus sign there, but that should be a plus sign, because when I take A and multiply it to, or distribute it through, and B and C distributing it through, we get A times X naught with a minus sign in front, B times Y naught with a minus sign in front. But then I move it to the right-hand side of the equation, and the minus sign disappears then, or I essentially add that to both sides of the equation. So that should be a plus sign there. That was just a typo. So that's the equation of a plane, the scalar equation of a plane. So let's go ahead and construct.
Sorry, can I ask a very quick question?
Yeah, go for it.
So the plane above is defined by R0, R, and point P or Q?
So the plane, this plane up above here, the very first one in part A, is we've got a point that's given in the plane. Maybe I'll color code these. We've got a point that's given in the plane. That's our point P. And we're also given a normal vector to the plane. That's n. So those are the two bits of information we're given. So in our equation, that's the n value here. That's the vector that we're given. And the point we're given as a position vector. So that's our R naught. So those are the two givens, that and that. And the R is just an arbitrary position vector of a point in the plane. This is the equation that it has to satisfy. If I take that arbitrary point, so for example, suppose I want to know, is the point 10, 10, 10 on this plane? Well, I'd take for R, I'd plug in the vector 10, 10, 10, and I'd see if I take its difference with R naught, which is the point I know on the plane, and I dot it with n, which is the normal vector I know, do I get 0? If I do, I know it's on the plane. If I don't get 0, it's not on the plane. So this equation is giving us a condition that R has to satisfy in order to correspond to a point on the plane. Does that make sense?
Yeah, totally. Thank you.
You're welcome. So R's are variable and the other ones are constants. So let's go ahead and see how we can put this together. So we've got a point, and we're told that this plane is parallel to the XZ plane. So this is where we think, what do I need to know in order to define a plane? I need to know a point and either two other points or two vectors parallel to the plane or a vector normal to the plane. So maybe I'll try to seek these two things out. Do I know a point on the plane? And the answer is yeah, because we're given it, 5, 7, negative 6. So we know a point on the plane, 5, 7, negative 6. Do we know a normal vector to the plane? Well, the vector is parallel to the XZ plane. So there's X, there's Z, here's Y. The XZ plane is this plane here. So that's our XZ plane. And it has a normal vector that points in the J hat direction. So that's the normal to that XZ plane. So because I know my plane I'm looking for is parallel to the XZ plane, and the normal vector to the XZ plane is J, then that must also be a normal vector to the plane I'm looking for. So I can read from that statement that I've got a normal vector for my plane. So now we've got point, vector, and so now we can put it together into the equation of a plane. Equation of plane. So our equation of the plane is going to be, we take our normal vector, 0, 1, 0. We dot it with x minus the x coordinate of the point we know on the plane, y minus the y coordinate of the point we know on the plane, z minus the z coordinate of the point we know on the plane. And that dot product has to be 0. And so this becomes then, when we do the dot product, we get a y minus 7 is equal to 0, or a y is equal to 7. So there's the equation of our plane. If it's parallel to the xz plane and it passes through the point 5, 7, negative 6, then it's got to look like this. It's got to be a plane that sits in space like this and passes through the point y equals 7. So that's the plane we just found. Consists of all points satisfying y equals 7. So this is typically how we're going to work with those equations above. We're going to find a normal, we're going to find a point, and then we're going to write down the dot product and then expand it out. And we didn't necessarily have to write down the dot product immediately. I could have written 0 times x minus 5, 1 plus 1 times y minus 7, plus 0 times z plus 6 is equal to 0. And maybe I'll do that in this next one, just to see that we can always skip the dot product step if we really understand what the equation is actually capturing here. So again, we're interested in a plane that passes through a point and parallel to another plane. So I want to find a plane that passes through the point 514, and I want it to be parallel to that plane. Can I figure out, because it's parallel to this plane, what the normal vector has to be? What does the normal vector have to be? You got it, yeah, 2, 3, 4. So the idea is we know it's parallel to this plane. So the plane that we're given, maybe it looks like this. I'll just draw plane in space. Maybe the plane we're given looks like this. And so its normal vector, which we can read off of it, would be 2, 3, 4. That's the nice thing about the equation of a plane, is we can immediately read off its normal vector. The plane we're looking for has got to be parallel to it. So it's going to look something like this. And since it's parallel, it also has to have a normal vector, 2, 3, 4. And so that's our normal vector, 2, 3, 4. And therefore, our equation of our plane is going to be 2. This is where I said you can sort of suppress the dot product line and just go right to the meat of the problem. It's 2 times x times the x coordinate of the point you know on the plane, plus 3 times y minus the y coordinate of the point you know on the plane, plus 4 times z minus the z coordinate of the point you know on the plane. And that's got to equal 0. And so in this case, we get 2x plus 3y plus 4z is equal to 10 plus 3 plus 16, or 2x plus 3y plus 4z is equal to 29. And from this, we can see that the equation of the plane we were looking for almost looks like the equation of the one we started with. It's a 2x plus 3y plus 4z. And that's just because they're parallel to each other. That's what information is being captured there. They have the same normal vector. The only difference is, when I write the equation in this way, what that value is on the other side of the equality. Here it was 29, whereas above it was 0. So that's the only difference. All right, so that's a couple of examples using our normal vectors. Now let's bring the lines into the mix here. Suppose I have a plane that I want to pass through the point 2, 4, 6, and I want it to contain this line. So I need the plane. Maybe it looks something like this. I want it to contain the point 2, 4, 6. And I want it to also contain the line. We'll write the line like this. So there's our line, which is x equals 7 minus 3t, y equals 3 plus 4t, and z equals 5 plus 2t. So that's the plane I'm looking for. It's got to contain that line and contain the point 2, 4, 6. So again, we have to think, what do I need to determine the line? I need to know either 3 points on the line, but even if I have those 3 points, I'm still wanting to go with, then I need to know 2 vectors that are parallel to the line plus the point, or parallel to the plane, sorry, plus the point. But even then, I don't really want just 2 vectors parallel to the plane. I'd like to cross them and get that normal vector to the plane. So I'm really interested in getting a normal vector to the plane and a point in the plane. I have a point in the plane already, so now I need to find a normal vector to the plane. So I need to look for 2 vectors in the plane or parallel to the plane. So when I look at this line, I can use the equation to extract some bits of information. I can find a point on the line. That would be given by the 7, 3, 5, or in other words, when t is 0, I get a point on the line. So that's 7, 3, 5. So I know that's a point on the line. I can take t equals 1, t equals 2, get all sorts of points on the line that I want. But I'm really interested in a vector that points in the direction of the line. So I can also find this vector. This vector, I just read the other constants that are in the equation. In other words, the coefficients of the t. So this would be -3, 4, and 2. So that's a vector that's parallel to the line. So now I've got one vector parallel to the plane. I can get a different vector parallel to the plane. Maybe I'll do it this way so they both originate from the same spot. There's another vector that's parallel to the plane. How do I get that vector v? That's going to be tip minus tail. So that would be 7 minus 2, 3 minus 4, and 5 minus, sorry, I'm switching these up. Tip minus tail. I wrote the tip and the tail in the reverse order because I was going the other way. Tip is the 0.246. So that would be 2 minus 7. And then the y component, 4 minus 3. And the z component, 6 minus 5. So that becomes -5, 1, and 1. So there's a vector that is also parallel to the plane. Maybe I'll write down the u vector as well. So that's our u vector that is parallel to the plane. It was the one we got from the line through -3, 4, and 2. So awesome, I've got 2 vectors that are parallel to the plane. What am I going to do with them? What do I do with these 2 vectors now? I'm interested in getting I'm getting a normal vector, so I'm going to take their cross product. So we're going to go ahead and take v cross u. And so that would be the -5, 1, 1. And I'm going to cross it with -3, 4, 2. And as I said, what I like to do is just write -3, 4, 2 down below. You can do this however you want, whatever you're comfortable with. And so our cross product becomes 1 times 2 minus 4 times 1. So 2 minus 4 is -2. And then the next one is negative of -5 times 2, -10 plus 3. -10 plus 3 is -7. And then the last one is -5 times 4 is -20 plus 3 is -17. So we get -2, 7, and -17. And so there's our cross product. That's our normal to the plane. So this is normal to plane. And we have a point on the plane, 2, 4, 6. So now we're in good shape. Now we can get the equation of the plane. And the equation of the plane is going to be the x component of the normal vector, -2, times x minus the x component of the point we know, plus 7 times y minus the y coordinate of the point we know, plus -17 times z minus the z component of the point we know is equal to 0. And of course, I ran out of room on that side, so I'll shift it over a little bit. Is equal to 0. And there's our equation of our plane. We could expand it out and move that constant to the other side, but the bottom line is we found our equation. How do we get the vector v? We said there's a point. I'll put these in a different color. There's a point we know on the plane, and there's another point we know on the plane, namely that point that we can read off of the line by taking t to be 0. So I've got 2 points that live on the plane, so I took v to be the vector that went from the point I know on the line to the point on the plane, 2, 4, 6. Does that help? Does that answer your question? Perfect. All right, so that's it for today's lecture. We'll pick up the last example on Friday, and then we'll get into section 13.1. We'll come back to 12.6 later on, but we're going to get into section 13.1 because it's on parametrized curves, which is a very natural extension to equations of lines.